Hello, my name is Virgil Goldberg and this is my lab 1 on charge tapes. So as a little introduction, this lab has the purpose of visualizing the transfer of electric charges as well as a proof of the electric force between two charged objects. We'll then use a computational model to compare it with our initial experiment. And we will see that some real-life environment and have some interactions and do impact the final result, and we'll talk more about it later. So here are the physics principles. So first of all, we need to know what charges are. So positive and negative charges that it can interact and have forces in interaction between each other. So these forces can be found under Coulomb's law that is written here of force equals to k, the product of both charges over their distance squared. And for the sake of this experiment specifically, we also need Newton's law of gravitation, namely that force equals mg, as well as Newton's law that an object which has no motion has no forces acting upon it. So here is the experiment. So as a little overview, the system of this experiment was tape B. So this is what we were measuring. The environment are tape A that pushed the tape B upwards with electric field repulsion, as well as the earth and gravity. So we consider the tapes as point charges for this experiment, and air resistance is not taken into account, nor is any friction with any of these pillars. And both tapes are assumed to have the same charge. So here are the different steps of the experiment. So we created two charged tapes using this method of using a U-tape and a base tape to rip electrons away from it. And then we checked for the charge. We found that it had a positive charge by putting our hand after rubbing it in our hair or a jumper to find out that to make sure it was charged. Then we stuck tape bridge with tape B and used tape A with its charge to measure how much, we'll say, the distance to up until B became in equilibrium between the force of gravity and the force of the electric field. So here are the results. So here we can see our data, the tape mass that I just found from the internet for this specific tape I used, the distance between the tapes when it came to equilibrium, the charge of electrons, area of tape, area of atom. And with the calculations, we can see that the charge of the tape was of 1.05 e to the minus 8 coulombs. So this is the number of electrons used, and this here is the number of electrons, we'll say lost electrons for every certain amount of atom, which is 6.1 times 10 to the 6 atoms. So here's my computational model. So here we can see the constant variables. So we have the k value, the electrical constant, the charge of electrons, the gravitational acceleration, the mass of the tape, length, etc., etc. Here we have the calculations that resemble what we just did previously here manually for the experiment. We print out the result, and here are just the visual specification, for example, the spheres, the arrows, here. And here are the results we found. So the charged tape, this is the charge on the tape, the efficiency of electrons, and the ratio of atom to electron. So we can see that those results are extremely similar to the ones previously seen in our experiment. For example, here the charge of 1.05 e to the minus 8. Here we find the same value with slight differences. You'll see very limited differences. So if we compare both results, we see that once again they're very similar because we use the same base values. The calculations are the same. We just assume that the computational model uses the real-life values. But in reality, there are sources of error in this system because the tapes are considered point charges when in reality they are not. They are a plane of charge. Both tapes have the same charge. We also assume that, while in reality they do not have it because, of course, this is, we'll say, kind of a rudimentary way of creating a charged tape and not very accurate. There's also measurement issues in length, in width, in distances. It was very hard to measure as well, and we also do not take into account friction and air resistance in our experiment. So as an extension, what if electrons had positive charges and protons had negative charges? What would change about the observation you made with your tape and other charged object? Well, they would behave in the same way because both tapes, if we use the same principle, like the same preparation method, will both have the same charge, whether their protons are negative or electrons are positive, etc., etc. They will continue to repel each other as long as they're charged. We'll say they have the same charge. And the other question is, why is it important to handle the charge tape as little as possible? Well, it's because as soon as it touches something, it transfers electrons and gains electrons from whatever it touches. So if it touches a skin or anything, basically, there will be electrical interactions, even with air. Thank you very much.